Okay, so we want to evaluate the triple integral over q of 2x plus y dv. Q is bounded by, in space, by the cylinder y equals x squared. It becomes a parabolic cylinder. Y equals x squared in the plane is a generating curve. The plane's y equals z, x equals y, and z equals 0. So this guy, at least in R2 in the plane, it graphs to be a happy little parabola, right? This guy graphs to be the 45-degree line, x equals y or y equals x. And I know those guys kind of bound each other in the xy plane, right? So that's, if you extend it into space though, you need something extra to bound it. And we'll talk, that's given by the extra equations, which we'll talk about in a second. So I think we can get away with just drawing the region of integration in the xy plane here. And whenever you can, avoid drawing the space region, do it. Sometimes you can't avoid it, but if you can avoid it, do it. So x, y, I know that y equals x squared, at least the part I'm interested in the first quadrant looks like that. And y equals x, a little skinny there, but looks like that. So it'll be y equals x on top, at least in the region I'm interested in, and y equals x squared on the bottom. I know that the intersection point is 1, 1. If you didn't know that, then you could solve the system of equations y equals x squared and y equals x, and you'll get that. And also 0, 0, right? So that's just the beginning of it. Now, in space, you could imagine translating that region up and down parallel to the z-axis. You'd come up with some weird-looking solid, right, that never ends. So it's got to be bounded on top and bottom by something. What bounds it on the bottom? That's the bottom bound in space, the xy plane. So that's, this interior part of that region right there. On top, it's got to be bounded by the plane y equals z. So that's just the ceiling. Okay, so let's set it up. We get the triple integral. 2x plus y is our integrand. dz, dy, dx. There's no reason not to go with the standard order of integration. So the limits of integration go from floor to ceiling. The floor has to be in the xy plane, z equals 0. The ceiling has to be y equals z. Oh, so what do we put in for the limit of integration, z or y? Y. It's always going to be the next variable out, or possibly a function of the both outer variables, right? And then the rest of it you set up like a double integral, where you have a vertical representative rectangle. So the middle limits of integration, the middle bottom limit will be given by the function that gives the bottom of the rectangle, which is x squared. The middle upper limit will be given by x, the function that gives you, or the formula that gives you the line in terms of x. And then what does x run from? 1 to the x coordinate of this point is also 1. Or sorry, 0 to the x coordinate of this point is 1. Wouldn't make much sense if it ran from 1 to 1. And that's the setup. Do you want to see me evaluate that? That's good? Okay, so we'll stop there. That's the setup for that integral. In this problem, we've got the integral from 0 to 1, integral 0 to 1 minus y, integral 0 to 1 minus y squared dx dz dy. We're not going to evaluate this thing. We're just going to sketch the solid of integration, which we often call Q. Now, in order to get the solid of integration, we need to use those bounds given by the limits of integration. So let's start with x. X lies between 0 and 1 minus y squared. Z lies between 0 and 1 minus y. And y lies between 0 and 1. I think the zeros are pretty easy to imagine what they are, right? So for instance, x equals 0 is really the yz plane, or part of it, right? Yeah. And so it's really the other equalities we're interested in. So let's start with x equals 1 minus y squared. Okay, what is that thing? Yeah, and you want to think in the plane defined by the two variables in the equation, the xy plane. Start there. And it is a parabola, right? So let's graph that. If it helps, draw yourself a little sketch. It's not necessarily something I need to see, but draw yourself a little sketch in the xy plane of what this thing would look like. So x equals just y squared is a parabola that opens sideways with vertex at 0, 0, right? You put a negative in front, it opens to the right. If it's positive, x equals positive y squared. The negative in front of it makes it open to the left, and the 1 is going to move it to the right, isn't it? Yeah. So you'd get, if this is 1, 0 right here, you'd get a parabola that opens this way, wouldn't you? So, okay, let's translate that into our solid in space and realize I think we can stop it, everything in the first quadrant. So this had to be at x equals 1, right? 1, 0 for the vertex. So I might do this. Let me move this guy a little further out that way. We'll see if that looks good. So I might put 1, 0, give myself a little bit of space, put it here. And then, where's this? So everybody look up here. Where is this intercept at, the y coordinate wise? So yeah, if you plug in 0 for x, well, yeah, this one down here is at -1, but the one on top has to be at y squared equals 1 or y equals 1, right? So I'll go up to 1 on the y, something like that. And I'm just going to draw this part in my space picture. A little too straight. I kind of missed my coordinate, but I could always make my hash mark bigger if I missed it, right? Okay. Okay, now what do you do with that generating curve? You translate it, really in reality, if you wanted the entire graph, you'd translate it up and down parallel to the axis that corresponds to the variable that's missing, in this case z, the z-axis, right? We only need to translate it up a certain amount. Again, I can tell that because of all these zeros over here. But before I do that, let's look at some other stuff. But the idea is eventually I'm going to translate this up to get part of that parabolic cylindrical surface. But let's go and look at z here. The equality z equals 1 minus y, in fact. So let me see if I can create a little bit more room here. Maybe make that just a bit smaller. Okay. So z equals 1 minus y. What does that graph to look like? It's got to be a plane. Anytime you have z to the 1 power, y to the 1 power, nothing else except a constant, it's a plane. And you can actually, in the yz plane, graph the line that it corresponds to in the yz plane, right? That's not hard to do. So just find intercepts, because we're just graphing the part in the first octant. So if y equals 0, what's z equal to? So I'm going to do this one in red. And then if z equals 0, what's y equal to? 1. So the generating line, the line segment, the part of it I'm going to draw, it's just that. That really is a generating curve, a straight curve, as well. And you can translate it in general forward and backward along parallel to the x-axis, right? So can you imagine what this thing is going to look like based on these two 2D pictures that we drew? So I haven't even looked at these limits yet, and I will in a second, but I can imagine it's almost like a lean-to coming out this way, right? That's the red, it'll be a plane in red. But then the cylinder in green is going to cut that thing as it goes upward, right? So what would that look like? Well, there has to be a line of intersection, or a curve of intersection, rather, that lies on both the plane that's going to be in red and the cylinder that's going to be in green. So if I were just drawing the cylinder, okay, I would go up like this, put a copy of this curve here, and it would look something like this, wouldn't it? And it would keep going up, but I stopped it there at maybe a height that's close to 1. Actually, from this perspective, it's a little above 1, but I stopped it there. I'm probably going to do some erasing anyway. Right? Okay, so actually, let me erase that for now and just leave that there. So actually, let me erase it just so you can see what's going on. And then if I just draw the plane in red, it would come out like this and look something like this, right? I'm actually going to leave that part in there, and then I think it'll help you imagine what the solid will look like. I'll erase that extra stuff in a second. So now, what's the plane in red? This is the face of the plane we're interested in, right? And so if you bring up that generating curve in green, translate it upward, then you get, it'll intersect right here with the plane, right? Right on the XZ wall, if you want to call that XZ plane a wall. But then what does the generating curve have to look like? Without actually finding it, it has to lie, they have to intersect here, right? We see the curve in green and the generating line in red, they both go through 1, 0. Technically it's 0, 1, 0. 1 on the y-axis. So we know they're going to intersect here. We know that, in other words, the cylinder is going to intersect the plane here. Green intersects red here. Green intersects red here. And the intersection curve has to lie on both the plane in red and the cylinder in green. So it has to curve down because it's on the cylinder, and it has to lie in the plane because it's on the plane, so it's going to have to curve down like that. And now I'm going to erase the extra stuff. The stuff I don't need. Maybe I ought to use the stroke eraser. No, that's too dangerous. I can't do it. It's too dangerous. Okay. So the part I'm erasing right now is extra. So can you see that it's bounded in front by the cylinder? And then it's going to be bounded on top. The ceiling is going to be the plane. The extra part where z goes from 0 to 1 just kind of falls out of that. I'm sorry, y goes from 0 to 1, just kind of falls out of that. You can see, yeah, the intersection point here is at 1. So let me finish the idea here then. So then that's it. It kind of looks like a weird-looking wedge, right? A wedge from the plane that's been cut kind of laterally on a curve, right? And then this curve right here is the curve of intersection. And it's really critically important to get the curve of intersection if you want to really have an idea of what these surfaces look like. So there you go. That's it. And it's not supposed to be easy to imagine. It's not. It takes practice. So if you're having trouble with it, everybody else is too. Don't worry about it. Just practice and get as good as you can.